Hey class, this video is going to be on 6.18 graphing simple rational functions. So first, what is a rational function? A rational function is in a form like this, like f of x equals p of x divided by q of x, where p of x and q of x are both polynomials. Here's a couple examples of some rational functions. Now, these examples are not simple rational functions, which we're going to be looking at graphing today. Simple rational function is in the form y equals 1 over x. This is what we call the parent function of this of the simple rational functions. And when you graph a rational function, it makes what's called a hyperbola. And hyperbolas have these branches that are like mirror images of each other. They're actually reflected over this line here, the y equals negative x. And hyperbolas have what we call asymptotes. And you can see the one asymptote is right here, the y-axis for this one. And then the x-axis. So the branches approach the x and y axis on both sides, but then we'll never cross those. So their asymptotes are like the invisible lines that the lines where the function will not cross. And in this one, it's the line x equals 0, the y-axis, and the line y equals 0, the x-axis. So domain and range then kind of go along with that. Domain is, you can plug in any x that you want into this function, except for you cannot have an x equal to 0, because you can't divide by 0. So it's y equals 1 over x. And then for range, you'll get out a wide variety, all real numbers for outputs, except for you will never get out the output of 0. 1 divided by like 1,000 is very, very small decimal. It's very close to 0, but it will never actually equal 0. So that's the range. So any function of the form y equals a over x has the same asymptotes, domain, and range as the parent function. So anything where like 3 over x, 5 over x, anything like that in that form has the same domain, range, and asymptotes as the parent function. So then we're going to take it one step further, and you can translate simple rational functions. So if they are shifted, we think of this shift as our hk. So we kind of say like it shifts the entire graph. So we call it our new origin. The x equals x equals h is our vertical shifts. The h shifts the graph up and down, or the hyperbola up and down. The horizontal asymptote is y equals k. That shifts the hyperbola left and right. So shifting horizontally and vertically. So let's look at this example. This is an example of a simple rational function because it is just a constant number in the numerator of the fraction. There is no x value. It's not a linear, quadratic, or anything. It's just a constant. So we look at our shift first. Just like in all of our other examples when we worked with parent functions, the h comes out as opposite. So the h is positive 1, and then k is 2, because it comes from a over x minus h plus k. So our h is positive 1 and our k is 2. So I'm going to go ahead and go to the point 1, 2, and then I'm going to draw a vertical and horizontal asymptote that crosses at 1 and 2. Because that's going to be the point in which my hyperbola branches are reflected or mirror images across. And then we have our vertical asymptote then will be that x equals h, and that means it is x equals 1. So that's my vertical asymptote, which you can see on my graph. The horizontal asymptote is going to be y equals k. That's the horizontal shift. So it's going to be y equals 2. So those are your asymptotes. And then to graph this, so since we've already shifted the graph, we're going to take this shift off, and now we're just going to graph the y equals 3 over x. Except for that, we're going to pretend like when we graph just y equals 3 over x, we're going to graph this, and we're going to pretend that this is the origin 0, 0 point. So we're going to graph from that point being 0, 0. So I'm going to pick some points, x, y. You need to pick 2 points on the left and 2 points on the right. Since you're going to be dividing by 3, I usually pick numbers that are divisible by 3, like -3, -1, then +1, and then +3. I skip 0 because you can't divide by 0. 0 would be undefined. You could just pick -2, -1, 1, 2 every time, but then you end up with decimals. So plugging it in, 3 divided by -3 is -1. 3 divided by -1 is -3. 3 divided by 1 is 3. 3 divided by 3 is 1. Then I'm going to graph these points, but I'm going to graph them from this point 1, 2. So going to my shifted point, I go to the left 3, then down 1. There's my -3, 1, which is actually the point -2, 1. But with my shift, it's the point -3, -1. Then I graph -1, -3. And these two will make my one branch of my hyperbola. Now, the branch approaches this +2, so it's going to get really close up there, but never cross. And the same thing down here, it's going to get really close to this asymptote of 1, but never cross. Now, I'm going to graph my other side. I graph these points. So from my shifted point, over 1, up 3, and then over 3, up 1. And the same thing, so going up, you're going to get really, really close to this +1 asymptote, but never cross it. And then coming back down, get really, really close to the +2 but asymptote, but never crossing it. So then from there, I can find my domain and range, and they're going to correspond to my asymptotes as well. So my domain will be all real numbers, except for I cannot have x equal to 1, because my hyperbola gets really close to 1 but never crosses 1, and it goes back to my original. I can't plug in 1, can't be an input because I would get 0 in the denominator if I plugged in 1. So all real numbers except for 1. The range is all real numbers except for that y cannot equal 2, because that's my other asymptote through the y. So no matter what input you put in, the output will never be 2. It'll approach 2 but never equal 2. Okay, let's try one more. So the first thing you do is identify your shift, and then you use that as your new origin point. So this one would be opposite of h, so -3, k is the same, -1. So go to the point -3, -1, and then draw a horizontal and a vertical asymptote through that point so that they intersect at the point -3, -1. So then you can label your vertical asymptote would be x equals -3, and the horizontal asymptote will be y equals -1. Then I'm going to graph, but I've already done the shift, so now I only need to graph 2 over x. So whatever's left here after the shift. So I'm going to pick x, y points. I'm going to pick, this time I'm dividing 2 divided by x. So I'm going to pick -2, -1, +1, +2. So that I get 2 points of my hyperbola to the left of the shift and 2 points of my hyperbola to the right. Plugging in -2, 2 divided by -2 is -1. 2 divided by -1 is -2. 2 divided by 1 is 2. 2 divided by 2 is 1. So then graphing that, so from my 0, 0 point, so I'm graphing from this shifted point right here. I'm treating that as my 0, 0. I'm going to graph -2, -1. So over 2, down 1 from your shift. Then over 1 to the left, down 2. And then you use your asymptotes as a guide, because it's going to approach both those asymptotes and get really, really close to them but never cross. And then on the other side, you go from your shift point right 1 up 2, then right 2 up 1. And then use your asymptotes to help you draw your hyperbola. So really close, but not actual crossing. So the actual points from this hyperbola are like -1, 0, -2, 1, -4, -3, and -5, -2. So if I would have plugged these points into my x, into my original function, those are my outputs that I would have gotten. But instead, we use just like the parent function idea and use the shift as the origin. So domain is going to be all real numbers, except for that you cannot have x equal to -3, because that's your vertical asymptote. The range is all real numbers, but y will never equal -1, because that's my horizontal asymptote. Those will be the values that the hyperbola approaches but never reaches. And that wraps it up. So remember, a rational function is when you divide one polynomial by another, the denominator cannot be equal to 0. I used, for simple, I used the parent function. We graphed branches, which are symmetrical parts, like x, y, and then -x, -y. And then we use the hk for the vertical and horizontal asymptotes. All right, thanks for watching.